Okay, good evening all.
Hello sir, good evening.
Okay, so should we start now?
Yes sir, it's about 6-7. So I think we can start.
Yes, good evening Padmalata madam, and good evening everyone. Just let me share my screen and start. In between, others may join. Okay, I have shared some data files in Google Classroom, which you can download to practice the content discussed in today's session. Today I am going to discuss the feature extraction and analysis of signals, finding similarities between the signals, and if time permits, we will also go in the filter design today itself. Okay, so this is my presentation. Okay, so today we are going to discuss signal measurement, analysis, and feature extraction. And this is an important topic before we apply any machine learning or any algorithm, that we need to extract the features before applying machine learning or classification, deep learning, like that. So deep learning does this thing automatically. So therefore, in deep learning kind of application, the signal and this feature extraction is not important. However, for accessing the quality or enhancing the performance of the particular signal or output, we need to analyze it with some parameters. Okay, so this signal measurement is going to be that's kind of important. So signals can be in signal features can be in time and domain or in frequency domain. Then we'll see some signal similarities calculation like autocorrelation and other. So feature extraction is an important part, and it is the process of transforming the raw signal into some parameters. So if you have, for example, if we have a sinusoidal signal, then its peak value can be one parameter. So peak of this sinusoidal can be one parameter or one feature of the signal, and these features helps to get information about the signal without processing the complete data of the signal. So this feature extraction plays an important role in the machine perception kind of for the machines. If you extract the features, then analysis becomes easier for the computation part of. So for machine learning and machine learning kind of algorithms, this feature extraction plays an important role, and analysis of the signals is also important for evaluating the performance of any operation. Anyway, so what are the different features? Features, we say that features are calculated in time domain. So some of the features are statistical features. Statistical features are like I was telling about this peak. Peak is one feature, and peak to peak distance or peak to peak amplitude. So peak to peak amplitude, peak amplitude, and peak to peak amplitude. This is feature. Time period is one feature, and RMS value is one feature. It can be a mean value of the signal, and it can be kurtosis, skewness of the signal. These are statistical features that can be used for the analysis purpose of this. And there are some time related features also, that rise time or fall time, overshoot, time period, we can say. Any other time related feature? Feature is just a parameter. So time related feature or time related parameter in a signal can be rise time, can be fall time, can be a time period, or can be a pulse width, duty cycle. Very nice. So these type of parameters are time related parameters, and these are time related features. So time related, these analysis, this kind of analysis can also be used as a feature. So that is also one kind of feature. Any other time related feature anyone can suggest? Time related feature of signal. I'm not frequency. Yes, so I'm taking time period, so then that relates directly to frequency. So that is also something. Anyway, and then performance related parameters. Yes, delay time. Delay time can be one. Delay, phase difference if there is a phase shift, and like that. So, and the features, these features, whatever features I am telling, these are the general features. There can be specific features specific to the signal, like ECG signal have some specific features, PQRS kind of peaks and their peak to peak differences in PQRS, and these are the general features. General features can be statistical features, these can be time related features, and these can be some performance related features like signal to noise ratio, total harmonic distortion, like that. So some performance related parameters can also work as features, and in features are these all the time related features. So similarly, frequency related features, so features can be in frequency domain also. Frequency domain features, so many people use DWT, FFT for machine learning. and continuous wavelet transform, discrete wavelet transform. These all are used for the machine learning purpose. They do feature selection, that which features are more dominant in the analysis or in classification, but these works in frequency domain. And there is one more domain called time frequency domain, that is the DWT comes in the time frequency domain, short time Fourier transform and DWT. So this is actually time frequency domain. FFT is in frequency domain, but DWT is in time frequency domain. So these are the general features that people use for analysis. Okay, so here I have just given a sort of brief idea that the statistical features, local maxima, yes, local and global maxima, minima, local minima, global minima, these all can also be statistical features. Standard deviation can be also a feature. Transition features, overshoot, undershoot, rise time, fall time, like that. SNR, THD, performance related, DFT, DCT, frequency domain and time frequency, and DWT, like that. There can be many other features possible. It is not that features are limited to this, but these are the general features that are used for analysis purpose. Okay, so local maxima, global maxima, local minima, global minima, these all can be evaluated in the MATLAB. MATLAB have predefined functions for these all kind of calculations. Sometimes you may have to do some analysis, write some programs for finding out these values, but most of the time these will be available. Direct functions will be available for this. Okay, so these are the statistical features. So we can find. I'll tell how to find the local minima in the MATLAB, and the transition features also we will discuss how to calculate in MATLAB. So let us go to MATLAB and see how to calculate these features, and also performance features, then frequency domain features. Let me switch to MATLAB screen. This is my MATLAB screen. Okay, so I told you already have one data, XLS data, in your testdata.xls in your current folder. So we will start doing analysis on this data only, testdata.xls. For analysis purpose, when we are reading the data, then commands will be same, similar that we are already doing the data table testdata.xls, then sheet 1. So I already have that program. I think this program is there. Yes. So this program already we have gone through these things, read table and header 1 and header 2. I had modified, I think, so I have to change. Let me try, and I think header 1 was changed in the last practice, so but in this folder might be working. And then for finding peaks, the command is to find peaks. Okay, just up to this point we have already done, and next is to find peaks. So first thing that we are working that on statistical features, that is to find the local maxima. Local maxima in a signal refers to the points. Suppose there is any signal, and local maximum is this maxima also, this maxima also, this maxima also. So we are trying to find out these points. So to find maxima, we have to find peaks in the data. So that command for finding peaks is find peaks. And when you write this find peaks y, it will give you can take two outputs. One output, this PKS, this is the peak points, value of the peaks, and the second is locations. Okay, so let us execute this up to this point. you write the this thing and execute it up to this point, you will find peaks. You will be able to see here. I am plotting the signal. I will go to editor and click on run button. So this is the original plot. Because of this plot command, this plot is coming. Then the hold on command is there, so this plot will be retained, and on this plot only I'm plotting new plot, which is the peaks. So the value of x at peak points, at peak locations, and value of y at peak locations. I'm just plotting only those points where there are peaks. That's why LOCS, this LOCS is written in this. Okay. So what it will do? It will plot only the points where peak is there. Then x level is so RO, this RO, what does RO does? RO will make those points red, and OO means those points at circle. Red circles will come over the points. Okay, and there will not be any line. Why? Because we have not given any line specification here. If I give line specification, then those peaks will be connected by a straight line. Here I have not given any line specification, so line will not come. Only peaks will be red. So that you can see when I step in. No, sorry, sir. I have to just remove this. I have to come out of debug mode and just go to editor and click run button. Now see the peaks, all peaks in this signal are labeled. Okay, all peaks are available to us, and also that you can see in the figures that what are the maxima points in this signal. Okay, so these all look similar. All points look similar. So for the analysis, all points can also be used for analysis purpose, for classification, or for some special analysis purpose. But if you want to have only the global maxima, only the maximum point of this, then what should I do? How can I find if I want global maxima in this signal? Now I have the local maxima, all local maximas, a list of all local maxima as peaks. These are the points, these are the values of maxima in this signal. See, all are 334. Just you see, even like this, these are the values. So if there are multiple, okay, then how to find the maximum value? So that the function for finding the global maxima is just you have to put max command. Just a max can do this thing. You have to find the max value. So max value of y. Okay. So then I have done this in this program number 2. In second program, I have already calculated this maximum value. You can see here max. The same coding this is all the remaining coding is same. Just read the same table and header 1, header 2, and then plotting. And then now instead of finding the find peaks command, I am using here maximum command. It will give you the maximum value. So the global maxima. Here I'm calculating the second feature which I discussed, global maxima. We have already done local maxima in the last program, and here we are going to discuss how to calculate global maxima. So the command for that is max of data. This max of data is calculating the values and then I'm plotting just only the maximum value. Go to this and click on. So here it is, because in this particular data, the case is that these values are exactly similar. In that case, the first global maxima will be the maxima. Therefore, this is the maximum. This is the global maximum in this case. If data have been variable, and there are many changes in the curve, if data is like that, then you will be able to find the global maximum. Okay. So this is the global maximum point. Now the question is how to find local minima and local maxima. And there is no direct program in MATLAB for local maxima and local minima. Similar to find peaks, there is no find min command. So how to, if I want to find out the minimum values of this, we have done local maxima with the help of find peaks command, and a global maxima with the help of only max command. This command is giving you global maximum position in this data. And if I want to have the minimum local minima, all local minima means, suppose if this is the signal, if I want to find out all these values, so these are called peaks and these are called valleys. So if I want to find out these valleys, then what should I do? What is the way? Can anyone tell me that by using these two, can I find out? How can I find out? Just we have to reverse the signal. Now see, the maxima of this signal will be equal to minima of this reverse signal. So if I do transform this to this, then or if I transform, I want to find out this minima. If I do just opposite transformation, if I take negative of this, then it will convert to maxima. So minus of signal, minus of y will, if I use minus of y instead of y here, then I can find out the peak value in the minimum value instead of maximum value. Although min command is there, but find peaks is not there. Find values is not available directly in MATLAB. So find peaks, if I want to use the same find peaks command for finding the minima points in a signal, then I have to take minus y instead of y. Okay, so let me show you that also. So here you see that finding maximum point. So there is a little extension on find peaks only in this third program, that we are finding the prominence also. So okay, I will come back to this prominence and the point width. Okay, just see the minimum. Here I am in this program. I am find peaks. I am using find peaks with minus y. This will give you the minima points. Okay, and I will come to the prominences, what it means. Prominences, what it means, the width in this case, so that I will discuss. But here you can just understand that we can find out the minima points just by taking minus of y and then hold on and then plotting this. So I have plotted that also here. I will go to run. See, the program is not too much complex. It's simple, that we have already done, practiced. Just add this command. This will do your work. I have added WP also, so that is for different meaning, different purpose. But here our focus is on peaks and locations. So I have just plotted peaks, locations by using locations, the same thing. So I will just go to the editor and run this. See the minimum values, minima, points, values point of the signal are identified and been marked with the red points. You can see this thing. I think it is visible, or if it is not visible, I can show you like this. These are the points. See, the all minima points in the signal are marked with the red point. Okay, so this is the way to find out the minima points. Now let us discuss about this thing, this maxima point width. So the actually in the signal, any signal we have in the signal, suppose the signal is like this. So this is the one maxima, this is another maxima, this is another maxima. So this maxima, if I connect the maxima point with the x-axis, okay, and then at what point it is changing or it is starting to increase. This it is changing from, it is going down to, it is when it is going up, when it is starting to go up at that point. So this thing, this connection, this point to this point is called width, this one, and from this point to this point the distance is called prominence. So vertical distance, actually not this this vertical distance up to means of connection from going up, means from the start peak to next going up, is called prominence. So that are also, these are also parameters in the statistical. So width and prominence, these two also are calculated with peaks. Okay, so this is also peak is the minimum vertical distance. Okay, so this prominence I'll show you. I think it is there, but in this these values are there. Only the values are available here. This kind of width and prominences. So you can see the p value and w value. These all are also the same as number of peaks. 40 peaks, then 40 pulse width and 40 prominences will come. So these are the related parameters to peak. So additional parameter with peak, because many times they ask that this parameter is a new parameter, what are the new features that you have included. So that's because people include new features into the analysis. So width and parameters per prominences are new features related to peaks. Okay, so then next thing is finding the local minima, and finding the local minimum is finding the global minimum. So next thing is to find the global minima. To find the global minima points, a simple command similar to max, there is a command called min. Okay, so min means, this is I have just copied the same thing from the previous one. So This is not at all required here. You just have to put hold on after finding minimum into the data, and this hold on will keep the previous plot into the MATLAB. Then you just have to put this plot command. So, but if all the minimums are same, then it will mark only the first minimum as global minimum. The first minimum will be here. Okay. So that is the minimum point here. So minima, in this way we can calculate the minima, maxima, global minima, global maxima, and next parameter in the statistical parameter is mean value. So to find out mean, just to be a simple command is there, just putting mean in that. So just you can just put mean value for finding mean. Just command is mean, 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 and then so instead of min, here we will use mean to find the mean value. Okay, so this was the minimum point. So to find the average value, simple mean you can use for finding the average value. To find the RMS value, standard deviation in the data, we can use STD command. This will give you the standard deviation. See this, my standard deviation here is 79.4663. So standard deviation can be calculated by this STD command, and this skewness can be calculated as my skew, means skewness command. So skewness is there. So skewness is actually maybe some new for some people, but it's a standard parameter in statistics, and which is the measurement of asymmetry of data around the sample mean. And if the skewness is negative, it means that data spreads more to the left of the mean. If skewness is positive, that means the data is more towards the right side of the mean. And if skewness is 0, that means it is perfect in the middle. So let me execute this program and get the information about data. So here information is 3.5147. Skewness is, so that means this data is moved right side of the mean value. And what was the mean value? Mean value was here, I had calculated it here. So this value was 29. So this more data is more than 29. Just saying, it means it is more right side of this data. Okay. Next parameter is kurtosis. These are related to some statistics. So that is a measure of how outlier this distribution is prone to outlier. So normal value of kurtosis is calculated by this equation, k equal to expectation x minus mu to the power 4 divided by sigma to the power 4. The ideal value or normal value of kurtosis for normal distribution, this k equal to 3. Okay, so how it is calculated? It is calculated by just in MATLAB there is a standard command for kurtosis. You can just write kurtosis in the data with the kurtosis with the data points, whatever data points are there. So then this you can execute this, and you can see that kurtosis is 1 second. See why it is giving standard deviation. Oh, actually, I have named it that. That's no problem. Actually, that answer was kurtosis only. So the variable name can be anything. I've just not changed from the previous program. So this is actually 13.57. So these all data can be saved into a single Excel file that can be used for feature as a feature, and that can go for your machine learning toolbox or machine learning app or machine learning program. So in this way, this statistical features can be used. And let us see some the pulse related features, how to calculate the pulse related features. So here I have listed the pulse related features. So the pulse features are rise time, fall time, slew rate, overshoot, undershoot, pulse width, duty cycle, period of the pulse, like that. Delay time, or these all are the transition and pulse related features. So for that purpose, I had uploaded one signals in GCR. So you can download these signals from GCR, because that pulse that I was using in the previous data, this pulse, see here it is not good to analyze some suppose I duty cycle, if I go, then duty cycle will not be there because it is going for very less time, it's up. So that's not it's not good for the pulse type of analysis. Okay, but although it can be applied for this also, no problem. I have taken new data, so that the pulse analysis can be done properly. So here see that I'm showing the pulse and transition features. So first of all, we have to load the signal. So that signal, my pulse signal dot mat is there in my current folder. You can see in my current folder, pulse signal dot mat file is there, and one data for pulse signal is there. So this data, when I read this data, so when I execute program up to this point, then it will show a clock one. Clock one is there in the workspace. Sampling frequency is there and time one is there. That means these three things are there in this pulse signal dot mat. If you write in command window pulse signal dot mat, then it will load these three things. So these three variables are stored into that. Okay, is this clear till now? Any question, query?
No, sir, no questions in chat box.
Okay, good. Okay, so just this time I have taken one data pulse signal dot mat, and over that data I am writing these commands. CLC clear close all I generally write in the starting of every program, and then I am writing that plot time one, clock one, and time. So that is a plot of simple data. Clock data is there. So clock data is like pulse type of thing. So let me show you the plot of this pulse. So when I execute it up to this point, number 5, when you click on the any place in this numbers, it will stop it till that point. It will not execute further. Okay, so this execution will give you this voltage and time. This kind of result will come. So either you can take it into a new, if you want, you can take it as a if you get a difficulty, then in this live script, then you can write in the simple script also this thing. these commands. CLC clear, close all, load my pulse signal dot mat and plot the signal, and then execute. So I will save it at my 10th program, and this is the plot of the data. Okay, where we are going to see the rise time, fall time, and all those things. Okay, so we can write to that just rise time. This command is, if you want to find calculate rise time, then command is rise time. Just rise time, then you have to give the clock 1. So because clock 1 is the variable here, any variable can be there. So clock 1 is the variable of signal, and then it is asking that either you give sampling frequency or you can give the time. So I have the time available, so I will give time 1. Okay, and then go to the editor, run, press run, and see. Rise time calculation is done. So, but here there are some other things also coming with this in this plot, rise time plot. So, rise time command. This is doing some plotting some new some of the things. What it is plotting? It is plotting the rise time. See, this is the rise time. It is saying, and this is the signal. There are the lower cross. This is the upper cross, lower state, upper state, lower boundary, upper boundary, maximum boundary, minimum boundary. There are many things are coming. Upper reference and lower reference. So what are the meaning of these things? See, in the bilevel waveform, this is bilevel waveform, because it is going to negative also, and it is in the positive also. And so, or also it have only 2 levels, in fact, 0 and 5, something. So, but it is having some noise. So, because of noise, these levels are changing. So, these levels are, as these levels are changing. So, we need to find out the state level first before going to find out this thing, rise time. So, this rise time command will calculate the rise time, and it will also calculate the states. So state levels here, why it is showing? But because we can change the state level, there is facility in this rise time command that you can specify the percentage level, from what percentage to what percentage you want to go. You can specify percentage reference levels. For example, I specify 20 and 80. You can specify. Now let me execute this. This is figure 1. Where is there any error? There is no error. Oh, there is some error. Percent reference level. Actually, percent reference level is there. Okay, levels. Okay, so there was some mistake in that. Okay, now it is changed. See that I have changed it to 20. By default, it is 10% to 90%. I have changed it to 20% to 80%. So we can change it. Rise time. Now the rise time value, you can see, is this thing. These are the values of rise time. So the values are also changing. Similar to rise time, we can calculate the fall time also. The command is that instead of rise time, you have to write fall time like this. Okay, and you can execute this. So these are the fall time calculation. You can see that this now the highlighting points have been changed. Okay, so command is just rise time, fall time. Just you have to type the point which you want to calculate. Suppose you want to calculate the slew rate. Slew rate, I think everyone knows what is the definition of slew rate. Anyone can anyone tell what it means, slew rate of a signal? Okay, so those who have done this now timing analysis of signals, they can understand the slew rate. Slew rate in the means the change in the voltage with respect to time. So the change in the voltage with respect to time is measured with the in the MATLAB by using this command. That you have to here specify the sampling frequency also. So and suppose you can provide this sample rate. You can provide time also. So I think we let us apply slew rate command. So the command for slew rate, you can save also. If you want to save the fall time into a variable, you can write like this and execute. Then it will be saved into a variable. All the fall times of the waveform will be saved into variable, which can be used for your table of features, which can be pasted into the table of features. Okay, similar to that, rise time also can be saved in any variable. So just I have just here I will tell about the slew rate. And in these commands, instead of time, there can be the sampling frequency also. So both of those are accepted. Okay, so this is slew rate, or slew rate can be saved as R equal to slew rate log 1 in time. So like that. So this will this is actually the slew rate and rise time and 5 fall time calculation of this. Now I will load another signal. So I have to take one new program, and this is similar. So I just copy from here, and this is also just I'm taking another waveform to calculate undershoot and overshoot in the signal, because in this overshoot and undershoot, better signal for overshoot and undershoot is saved into the pulse signal to another data which have proper overshoot and undershoot, because in this overshoot and undershoot both are not properly visible. So I'm loading another data into MATLAB, pulse signal 2, and this pulse signal 2 data, I think in this the names are different for time, so I will just change time 2 and also clock 2. Now I think it should work. So this data is better for finding the overshoot and undershoot. You can see that these points where these are having some time response, means some overshoot and undershoot here. So here you can calculate overshoot and undershoot in a better way. So these are the clock signal which have undershoot and overshoot. So the thing is simple. Just you have to load the signal first, and after loading the signal, you have to use the command that find out the overshoot. To find out the overshoot, overshoot, you have to write overshoot function. Overshoot function over the clock to signal. But if I you can find out in overall also, and so let me tell you, I can give time also. I can give here the second argument can be time or can be sampling frequency. So this is giving the list of all overshoots. If you want to see the particular only a particular overshoot of the clock signal, then I have to specify the time in the clock, means the from which sample number to which sample number I have to go. For example, if I take sample number 90 to 300, just for example, I'm taking this. I don't know this thing. No, okay, just a bracket. See here, there are this is the part of the waveform. Only a part of waveform is selected where overshoot is calculated. Similar to overshoot, we can also calculate undershoot value of a signal. Just undershoot. Okay, so undershoot of the signal can also be calculated. We can calculate the undershoots, all the undershoots in the signal by just not specifying any value, and we can calculate a particular undershoot of the signal by just specifying some value. Okay. So all similar means what is the overall conclusion is that we can calculate a number of parameters related to signal just by directly giving their functions. By just specifying the functions, you can calculate the pulse width, you can calculate the duty cycle. So for duty cycle also there is command. You can just give the duty cycle command, that what is the duty cycle of this particular signal. Then it will give you duty cycle of the particular signal. Okay, I hope you all, I have shared this data in the Google Classroom, this all the data files, so you can practice these things with me also. Just typing these commands and you can see the results. Okay, and then these are the some special features. And if you want to compare two signals, for example, if you have so if you have here I can use a time also, sampling frequency or time. Both of the options are there. Either you can put sampling frequency fs, that is available in this workspace, therefore this is not showing error. If it is not available, then it will show you error. Okay, now I'm going to show you how to calculate the signal similarities. So what is the way to calculate signal similarities? Signal comparison. Okay, signal comparison. What is the way to do? How we do the signal comparison? Yes, Ania. One way is written by Srinivas Gagandeep, that correlation is the way to find out the similarities or to compare the signal. Okay, either you this very simple way is that just compare the data of one signal to other. If both are same, then the signals are same. Otherwise, if you want to see the percentage of similarity, you can calculate a correlation between the signal. Okay, and another way is that you can calculate the time period of the signal. If both signals have same time period, then they may be may be similar, time period or pulse width, like that. Okay, and there is a way of plotting. You can plot both of the signal, and the plots are same, then also signals will be same. So they are looking same, then you can do compare that plots and see the signals are same. Any other way? Time period or frequency? We can also see the frequency of the signal. Okay, so for that purpose, for similarities, I will load data that my six similar. So in this, there are 3-4 signals, and where we will do a little analysis on the comparison of signals, signal similarities. So to load this data, I need to have one function. I will write load my sig similar. You can write a dot mat with it, or otherwise MATLAB takes it by default. I think this will, if you first save this, you can give any name according to your convenience. You can see that the data is loaded into it without even writing dot mat. You can write dot mat also with this, but if you don't write this, then also MATLAB automatically knows that it's a MATLAB data. So dot mat is by default in the MATLAB. Okay, now I have written clear so that the previous data. What is happening? Just what is? Okay, so this thing. See this. This is the workspace. In this workspace, I have 2-3 sampling frequencies. I have 3 signals, one S signal, and sig1 and sig2, and these are the templates, 1, 2, 3 templates. So many signals are available here, and they have sampling rates also different, because they one have 7501, another have 2621, and sampling rates are here. Sorry, so one have 8192, another 4096, and 4096. So there are this one and this one is having different sampling rate. How can we compare these two? Because they have different sampling rates. So for the signals which have different sampling rates, we need to convert the sampling. We have to resample the signals, and then we can compare it properly. So if I plot template 1, template 2, and signal S, so template 1 is T1 and template 2 is T2, and signal is signal, so signal is S. If we plot these 3, so I have this one. I will take it into okay. Let us take one subplot. In the subplot, we will plot it. So, how many 3 signals I am plotting? So I have to take subplot of 3 signals. So subplot 3 rows, 1 column, and first one, and then plot T1 template 1. See how T1, so what will be the length of T1? So with that we have to decide that it will start, if it is starting from 0, then what is the numerical length of T1? Because we are starting from 0, whatever is the numerical length, we have to go -1 to that, less than that numerical, 1 less than the numerical length. And this is actually the time. So if I don't give, so let me write T1 only, and I want it in black color, so K is black, for black. So let me execute it. T1 is correct. Okay, T1 is available. T1. Okay. T12. Let us see the second template. T2. In this third plot, so let me change the color also. So this was black, then let me change to red. Second one is red, and third color can be any color you can choose. That's up to you. So third color is, let it be green, and third one is signal. Not got it. 3 and 3. Yes, should be 3. Okay, so then it will see this. These are the 3. So you can see there is any signal similar? Is there any similarity? I plotted three signals in this graph. They are having different data, and they are not looking. Signal is not similar to any template. So this first one is template 1, and second one is template 2, and third one is template 3. The signal is not similar to that. So the thing is that we cannot always determine the similarity just by seeing the signal. So if I try to find out the correlation, Srinivasa sir answered that the correlation is thing that can give us an idea that if there is any similarity, because the sampling rate is different and signals are different, then how can we compare them without any parameter? Just by plotting, no, we cannot compare that. These are similarities there. So I will try to calculate the correlation between these. So for correlation, what is the X-score? X-score is the function to find out the correlation between signals. So this is the function. Okay. So I will try to calculate this thing. Now let me calculate. So C1, for example, C1 is the correlation between the signal and template 1. So I will find out X correlation between template 1 and signal. What is the value for this? So I will just go to editor and run. These are the correlations. So if there is, these are the this is the actually this type of correlation is coming. C1, then C1 is having these many values. These are the X correlation values. So if I plot this C1 value and I will plot it, I will take a figure window, or I will take a figure window, plot C1. Again, I will calculate the correlation between the template 2 and just I am trying to find out that the signal is matching more to what? More to C1 or more to the template 1 or more to template 2? Can anyone tell me without knowing this analysis result? See, now results are available. So okay, I have to plot this also, C2 also. Plots. See the C1 and C2. Y range is actually same, but you can by seeing this C1 and C2, means figure 2 and figure 3, which you can just say that which signal is more similar to which is showing more correlation. Means this figure 2 or figure 3? Actually, figure 3 is more correlated to that means figure 3 is, means the area covered under the curve in figure 3 is more compared to figure 2. Therefore, we can conclude that this signal is more matching to template 2 compared to template 1. In this way, we can get one idea that which is matching signal. How can we get an idea of the similarity? That we can get idea from this graph. That which is the so there are this is the way of finding the correlation between the signal. Also, there we can calculate the periodogram of the signal. Can calculate the delay between the signals. Then find delay command can help that what are the delay between the signals, between the two signals. Then you can compare by the delay also that how much similar those signals are. Also, periodogram gives the frequency content that can be also used for the comparing two signals. For covariance, periodicity, we can find out the period like that. So that those things can be used for calculating the similarities between two signals. Okay, so this was the idea of feature extraction, and this correlation is also useful for the feature analysis. So this can be used as a feature, and if this is autocorrelation, can compare the same signal, so can find out the similarity of the same signal with the same with that. Y-axis is doubling. In figure 2 and 3, see there is actually compared to signal. Yes. So because this is actually operation over the signal. It's approximately double because this correlation operator is applied over the signal. So it's a kind of filter. It's an operator which increases the value. If you calculate the correlation between two signals, and then it increases because it's a repetitive kind of movement, kind of this convolution and correlation operators are similar. So as two signals move over the other in the convolution, similar to that, without the time, without flipping, if we rotate, that is a correlation in fact. So the in the convolution, the signal values increases because of convolution. In correlation also the values increases. So that is the reason why the values are increasing in this correlation. If you see this equation of correlation, it is performed. I will say if I remember as yk equal to summation k equal to minus infinity to infinity x of kh k minus n, like that. So it's an operator like this. So here you see this, there is a operation. This operation increases the length of this. So this is actually correlation operator that is doing the changing. Okay, so we have calculated here feature extraction thing. Now I will go to the filter analysis. How to do filtering in signals. For convolution, by step by step, I will share one document in Google Classroom. You can go through this. So this very basic thing. So I will not go through that convolution step by step. But of course, convolution is important in LTI systems, and that is the way how the signals or systems work. So see if in the system, if some input xn is there and output yn is coming, and this system have some parameters h of n, it is passing through a system h of n, then yn is equal to xn convolution h of n. If this h of n is a filter, if it is a filter, then this hn represent the impulse response of the filter. Okay, so the impulse response of the filter, or which is having the coefficients, the impulse response is having coefficients in the filter. So the filter coefficient, finding the filter coefficient is actually the designing of the filter. So finding hn, finding this hn is the design. So if you are designing a low pass filter, so this hn should be selected, or should be in this way, so that the output, the low frequency signals of input are suppressed, are passed, and high frequency are suppressed. So hn should be designed in, the value of hn should be selected and should be calculated in such a way that it becomes a output only the low frequency signals are available. High frequencies are suppressed. Just wait one. So in MATLAB, this just I am giving an idea of what filter is, and how the designing of filter works. So these are the things that we have to find out. These are the HN we have to calculate. HN is nothing but impulse response of the filter. Just I will show you one presentation over this. Just a basic presentation. So this signal here, in the left side signal had two frequencies. See, I have written normalized frequency here. So this is actually a digital filter. Filters are of two kinds. In general, and filters can be analog filter, or they can be a digital filter. Okay, so here just you can understand that there were two frequency components in this input, and this is passed through a low pass filter. So low frequency component is remaining here, and high frequency is suppressed. That everyone knows that things. And so the digital filters are much more very important part of DSP, and many cores and processors are having many digital filters inside their designs. Therefore, it's a very important part of DSP systems, and they find applications and signals in various areas: space, biomedical signals, in processors, in communication systems, in the data analysis science, in signal processing, image processing. Image processing also, there are 2D filters, and statistical analysis, in defense, in space, everywhere the digital filters find their applications. And this is what I was discussing, that HN is doing the thing. HN is changing the signals. And what are the filter specifications? So a filter have some frequency to pass and some frequency to suppress. So there will be a cutoff frequency of the signal. But in the digital filters, there you have to specify two frequencies. One is pass band as frequency FP, and stop band as frequency F of S. And there are ripples in the filters, design frequency responses of filters. So these ripples in the pass band, this region is called pass band in the filter, and this region is called stop band in the filter. So in a caption, it is see here in the magnified view, it is shown that there is ripple. Ripple means the variation in the output. Okay, and so if the variations in the output, these are in the stop band. This is the stop band, this is pass band. So in the stop band, variations are called stop band ripples, and pass band variations are called pass band ripples. Pass band ripples are measured by delta P, and stop band ripples are measured by delta S. Pass band cutoff frequency is this point, this point is omega P or FP, and this point where it meets to the stop band, this point is stop band as frequency omega S. I have written here omega P is pass band cutoff frequency, omega is stop band cutoff frequency, pass band ripple, stop band ripple. These are the specifications of filter. So you should know specifications of the filter before designing. Other specifications or other representations are stop band attenuation. So it may be calculated from the stop band ripple. So if any one of these two is given, that is sufficient. Transition width is sometimes specified, sometimes not specified, because this is also a secondary specification. If you know the pass band frequency and stop band frequency, then transition band can be calculated by omega s minus omega p. Sampling frequency is important. It should be given because digital filter works on sampling frequency, and if sampling frequency is changed, then filter will also change. The cutoff frequency of the filter will change. There is a region. Here you can see that fs by 2 is written. So the entire region from here to here is divided into fs by 2. So this is fs by 2, and then cutoff frequency is taken from that. So many times it is taken over the normalized scale between 0 to 1. That means we consider 0 as 0 and fs by 2 as 1. So if cutoff frequency is fs by 4, then it will be 0.5, like that. These are the filter specifications. Okay, so digital filters are analog. The filter specifications are for digital filters. Filters can be analog filter, passive filter, RC kind of filter, and it can be a digital filter. Digital filters are better because they are reconfigurable. They work on software as well as on hardware. Digital filters are less noisy. They are customizable. You can increase the size of the filter. They have less ripple, less noise, more noise compression capability, noise suppression capability. Okay, so this is the digital filter. Then this can be digital filters can be of FIR type and IIR type. An IIR filter represented by this equation, numerator and denominator, there are poles and zeros both, whereas in FIR filter only zeros are only poles are there, zeros are not there. So there is no feedback loop in FIR filter. This difference equation you can see in this equation, there is no feedback loop, whereas in IIR filter there is feedback loop. Therefore these are comparatively unstable, but there is no feedback, so these are more stable and inherently stable. They have linear phase. So, and these filters have non-linear phase, recursive in nature. So these are non-linear filters, and these are the linear filters. So as IIR are recursive filters, and FIR are non-recursive filters. So that is the, and Butterworth and Chebyshev, these are the two types basically in IIR. These are available in IIR. So what is the difference between Butterworth and Chebyshev is that Butterworth have a smooth transition, slow means that. So in Chebyshev, sharper transition. It's not so sharp that I have made, but just for understanding, if there is a Chebyshev, then there will be a sharp transition. If it is a Butterworth, then there is smooth transition. And now in Chebyshev also you might have seen that there are two types. Chebyshev 1, so Chebyshev 1 I say, and Chebyshev 2. Two types of Chebyshev filters are there. So first type of Chebyshev filters have more ripples in passband. So Chebyshev 1 means passband, and Chebyshev 2 is stop band. So it's a ripple. It depends on the ripple. If ripples are more in the passband, then it is Chebyshev 1 kind of filter. If ripples are more in the stop band, then it's a Chebyshev 2 kind of filter. So that's a main important difference between Chebyshev 1 and 2. There are others also, the other differences and other reasons also for their names, but this is a main kind of thing. Okay, so we can connect filters in series, we can cascade filters and get better response, and this is always there. So cascading is possible in the filters. You can combine filters together and you can get a better response. That is okay. So this is one example of FIR filter. Okay. Now, I would like to go through the approaches in the FIR filter design. See, FIR filters design have been started from the time when digital processors and digital techniques, digital ICs was started. Windowing techniques are actually very old technique. So 40 years before, in the 65 to 72 time, these techniques were used in the design. And then sampling methods in 74, they developed one sampling. Still in the textbooks, our textbooks, only these methods are there, which were used in the 72. There, some of the books and some of the syllabus are using, they are giving sampling method in the curriculum, but sampling method many times they don't give. Then Parks McLaren, this was a very, very important revolution in the FIR filter design, and they used the one Ramage iterative algorithm for their design. So this is the, so these all are available. This is also available in MATLAB as a single command. Just by typing single command, you can use the Parks McLaren method for designing the filter. I will show you. Just wait for some time. Just after some time, I'm going to show you how to use this. Then in 1995, when genetic algorithm was developed, from that time, evolutionary optimization algorithms, or you can say modern algorithms, these optimization algorithms are being used for FIR filter design. Genetic algorithm, taboo search, PSO, ABC, harmony. This list is not ended here. This is continued. Means 100 every year, around 50 or 100 or 100 or more than 100 means around 100 publications are there in this this kind of FIR filter design only. And the applications of FIR filter design, these are countless. There are many publications in this. So it's going on. The design approaches are improving every time. So that's what this is an idea that how FIR filter design approaches are going on. So we are teaching to the students up to this point only windowing techniques. Okay, so IIR filters are designed from the transformation. So from the analog, there are two methods. You can design directly in the frequency domain. Also, and one method is that then you can do the bilinear transform. One method is that you design in time domain and then transfer to Z domain. So that is the bilinear transformation is there for doing this thing, for designing the IIR filters. This is the way. So there are two approaches. One is the designed filter, IIR filter designed in the analog and low pass filter, then apply transformation. First S to Z, then S to Z, again filter transformation. This is again here frequency band. These two ways are there in the filter design. Okay, so this was just an idea that what filters are and how filters are designed, how it is. So similar to FIR filter design, there are many techniques in IIR filter design also that can be exercised. So I will now show you the how can we design FIR filters. The definitions I have already discussed with you. So I'll just close the slide, so minimize it, and let us go to MATLAB. This is here, and I will go to my filter design session. Here, and I have one I'll show you this simple design. First of all, let me tell you how this I will not go through the internal details of this program. First I will just execute this and show you that. Just I will close all. Again, I will open it. I will just execute it and see whether it is working or not. So it's working, and see, this is figure 5, filtered signal and original signal. These are the original signals. This is the original signal, FFT of original signal, and this is FFT of filtered signal. So which filter is working in the background in this in the background of this program? Let me show you. I hope you are able to understand this these two figures, that this here it is not normalized between 0 to 1, it is normalized between 0 to pi, and it is also normalized between 0 to pi. So therefore it is showing the values from 0 to pi, and just a low frequency band is here and a high frequency band is here. Two bands are there in this signal. So which signal I have generated, I will show you that which I have taken the FFT of which signal. See, this is I was designing a filter with 250 Hz cutoff frequency and 50 Hz transition width, 80 dB ripples in the passband. So the design currently working is Hamming. I have written Hamming window. Just I am showing you windowing technique. So I have written one program, MyHamming, here. Another program is there for MyHamming, which is generating filter coefficient H_1, and these filter coefficient I am using to plot. So to plot the frequency response. I will show you MyHamming also. See, the program for Hamming window is here. Just I have written this Hamming window, and I have applied the signal to this window, and the filter coefficients are calculated with the equations that works on the Hamming window, that deals with the Hamming window. So that way. Okay, so this is the Hamming window, and that is giving H_1. So filter order is automatically coming to 66 order filter. You can see that 66 values are there in this H_1. That means that this filter order is 66. I have written programs for Kaiser also, for rectangular also, for this window also. Then frequency sampling method also I have done, and then this Sparks Maclellan also is there in the same program. I have written function for them, that particular method, and then I have called here. So I'm using 2 here. I should just comment 1. So only one method will work. I'm just keeping one method on, and remaining all commented. Commented means they will not work. Okay, now what I am doing, see this. This time I'm just telling you how to generate signal, and then how to apply the filter into the signal. Okay, so just try to understand this program. Here I have generated n values. First, the values of n are from 0 to 1000, and values of x. See, this is just a index number. Leave it. So x is actually a signal, because discrete we need index value, some discrete index. So that is why I have taken this n, and x is actually the signal. So x is calculated by a cos theta omega pi n plus b sin omega pi n. So omega is actually the frequency. Omega is actually the frequency. So I am taking 0.025 pi as first component and 0.07 pi as second component. You will say, sir, what is this frequency? You are taking in 0.7, 0.25. Is this the frequency? No. No, this is not a frequency. Actually, this is a normalized frequency. So 0.25 means if I have 1000 sampling frequency at 1000 hertz, then this 0.25 means 250 hertz. So first component will be 250 hertz. If I take 1000 hertz as a sampling frequency, it takes actually 2 times. So if I take 2000 hertz as sampling frequency, then fs by 2 will be 1000 hertz, and the meaning of 0.25 will be 0.25 will be the 250 hertz frequency. Just try to understand this concept of normalization in the digital filters. What is there, that we actually design filters not for particular frequencies. We design filter between 0 and 1. Okay, so if you see the research papers of digital filters or results of digital filters, you may see that filter is designed between 0 and 1. Okay, so what it means, what is the meaning of 1? 1 means fs by 2 is here. So if fs is 2000 hertz, then fs by 2 is 1000 hertz. So if your cutoff frequency is 0.7, that means this 0.7 multiplied with 1000 hertz. So if your cutoff frequency, a passband cutoff frequency is 0.7, that means 0.7 into 1000. What it means? 700 hertz. So 700 hertz actually the cutoff frequency. That is okay. 2 pi f is okay. 2 pi fn equal to okay. So that is okay. Actually, we take omega n only. So omega is 0.25 pi. Okay, that is okay. So 2 pi f. So okay, that is okay. But what I am telling that it means 700 hertz. and this 0.25 means 250 hertz. And if the frequency, sampling frequency changes, if I make it 4000, then these values will also double. I don't have to make a new filter, but same filter will work for different frequencies also. That is the meaning here. Okay, this signal is also generated like that, because I need to do analysis on the same basis, because this signal is also discrete signal here. Okay, then I have plotted this stem x. Stem x will be the plot of the signal. So here I have plotted this signal only. Now filter command that works on convolution. Filter command is there in the MATLAB, and also we can use convolution, because filtering is nothing but a convolution only. So in filter command there is facility that you can give the numerator and denominator, because it is designed for IIR and FIR both filters. Therefore, the first argument of this function is h, or the numerator values, and see in the IIR filter the function is like the sum expression in the numerator and some expression in the denominator. The coefficient of numerator are b and the coefficient of denominator are a. So in IIR filter you will get b and a here, but in FIR what happens, only numerator is there, denominator is not present, denominator is 1. Therefore in IIR filter, in FIR filters we write h here and the second argument is 1. Okay, that is why here 1 is written. Now here I have tried to convert the actually omega into the real values, so that is what is happening here. So you don't have to worry about it. Just you see the FFT. I have taken FFT of x and then FFT of y. What is x? X is input. So that is the FFT of input. And what is y? Y is the output. So here y DFT will be FFT of output. Okay. Now I have plotted frequency and x DFT. So that is original signal. So length of x only up to the length of x, because it is repeated. What happens when you perform this transform, Fourier transform or something, then they provide mirrored signal. That is why I have taken half of the signal only. Otherwise there will be mirroring. So one mirror will also be available. Therefore only one. So for that I have taken half of the length of this FFT, half of the length of the FFT. So now you might have understood the point that why I have taken here x by 2. And then hold on means keep this. Hold on is not there, not activated. Hold on is not activated. New figure I am taking for plotting the output. An output also I will take half of it. So this is the original signal and filtered signal. But this much small. This much small is program. Actual program is this much small. But to run this program, this is just a testing program kind of thing, that whether filter is working or not. So for testing, filter, you need filter. What is filter here? Filter is these values of h. So finding out these values is actually the designing of filter. What are the ways of designing filter? There are many ways of designing filter. The very basic way to design a filter is windowing technique. To calculate the coefficient with the help of window. Rectangular window is very much basic window. So let me go to the rectangular window design. If I have done it, here. Let us see the rectangular window. I might not have done this thing. Rectangular window is very basic window, and because I need to compare, yes, it is there. This problem 3. So problem 3 I have written here. I can go to the program directly. There is program of rectangular window, this one. So this is the program of rectangular window. Okay, so here I am doing the calculations for calculating the coefficient of rectangular window. Actually, this boxcar function, what is a rectangular window? This is a window where there is actually this kind of box. So in MATLAB there is a function called boxcar, and boxcar, this will create a boxcar like this. So that will be one rectangular window. So that window is to be multiplied. Here is a dot multiplication with the HD ideal filter, ideal low pass filter. So what we are multiplying it with the ideal low pass filter, and then whatever the result is coming, I'm taking it as B and A equal to 1. Then these things are okay, but it's not always required. The other things are not required. What thing we need? We need actually just a calculation of H. See, other things are extra calculation just for seeing the window, rectangular window only. Okay, and actually we need H only. So if H is calculated, then we can go for the our filter evaluation. Here what I have done, there are more programming is done just to see the window. So I am plotting the window. I am seeing the window, that how does it looks. So that is my own experimentation. In fact, we want up to this. Just we have to get the actual rectangular window. So rectangular window can be found out with the boxcar function. Okay. Then any question?
Sir, we are about 5 minutes left.
Okay, if there is any query question, then we can take. And okay, sir.
Yes, dear participants, if you have any query, any question regarding today's session, as today's topics were advanced on filter designing apps and other things. So if you have any query, confusion, you can ask, you can write in chat box. And we are here for the next 5 minutes to guide you on those topics. Dr. Atul Dwivedi sir is here. Yes, please.
Sir, H is alone, H is a variable or some value you're telling. Can you explain that, sir? That part only, we have to use it in the syntax. So H you are calculating. So
yes,
it is going to be an array or just a constant value or what?
actually it is going to be an array. It's a array of filter coefficients. See this one. No, it's not one. So what we see the equation of FIR filter. This is actually yn equal to summation of xn to h of n. This thing actually works. What I can say that filter coefficients. Hn is the filter coefficient. We are dealing with the signals. So x input is also a vector, an array, and output is also an array. In between, whatever the box is, this black box, h of n, this filter, this h is also an array. So x of n is an array, yn is array. The yn is actually convolution of xn and hn. So hn is also an array. So this array of numbers or array of coefficients of filter need to be calculated. That is what is called design of filter. So for this purpose, I will share one document in Google Classroom today, so that you can go through that document for understanding these techniques, all windowing techniques, or also the MATLAB programs, simple programs are there in that particular document, so that you can just type and see that how it is working. Actually, there is a background concept behind this particular work that I am doing, so that is actually that is working here. Okay, so here you have seen this rectangular window. I will run this program separately. See this. This is the rectangular window. Rectangular window means a box kind of thing where the values before this 0 point are all zeros, and after this 18 points are all zeros, and from 0 to 18 all values are 1. So this is a rectangle. A rectangular window it is called because its shape is a type of rectangle. So we know that the transform of rectangle is sinc function. If you transform rectangle from one domain, either from time domain to frequency domain, it gets converted to the impulse response. So the ideal impulse response of this rectangular window is a sinc function that is coming here. Just I will plotted that only. See here, after calculating this window, this h, I have converted it into the frequency domain, and seeing the response. So it's actually that is a frequency domain response of rectangular window. Okay, so this is the way you can calculate for the rectangular window. If you want to see other windowing techniques, so that is similar way to create other windowing techniques. I will rather discuss, I think if we get time, then in the optimization module, that how to apply this genetic algorithm or particle swarm optimization to generate filter coefficients. Because the better coefficients are generated, better filter design will be there. There are ripples in the when we see the frequency response of filter. If I show you the filter, see this is actually in the. I will show another. There are many designs that I have done. So if you see, this is actually dB plot. See currently, see, this is the dB plot of filter response. So you can see that there are ripples. There are variations in the this stop band. This is pass band. This is stop band. There are variations in the stop band. These are the ripples. So there are we need to minimize these ripples. So to minimize these ripples, these are the ripples. So if we see this also in the normalized domain instead of dB. Instead of dB, if we convert it into 0 to 1, if I convert it into the normalized range 0 to 1, it can be converted. So then there you will be able to see the ripples in the pass band also. So minimization of pass band ripple and stop band ripple is the goal of filter design. So better the H value, better this result. Also, this ripples reduces with increasing the order, but higher order filters result in the more hardware requirement and more power consumption, because if hardware is increased, then it will be power hungry. So nowadays every designer wants low power design, so they want to reduce the filter order. So filter order should be smaller, as minimum order filter should be designed. So that is why there is always designing compromise. Always it is challenging to design a proper filter. Therefore, optimization, multi-objective optimization, and evolutionary optimization algorithms are required to solve this. And as we see that this filter order is also very high. You can see that this filter order here, this is 66 order. So this is very high. This need to be optimized. So for that purpose, genetic algorithm or particle sum optimization or other optimization process should be applied to that. That will do the minimization.
Filter order and all will be frequency range dependent, sir? Or it is that always we should work for only lower filters? H should be lower.
Yes, H should have less number of coefficients. So that is the requirement. And the traditional designing methods like windowing technique, they had fixed that this equation of order calculation, they have one equation of order calculation, that is the order. But the modern techniques, they can reduce this order.
So there is a question by Dr. Suresh sir. Can you tell about the zero padding of time domain signal for FFT STFT?
Zero padding, yes.
I think this is last question for today.
Yes, zero padding in the STFT and DFT is done. So that is actually much more visualized in the image processing. That how does zero padding helps in convolution? And the size, how that the size of the output after FFT is decided based on the these things. So I think you can, and just let me see that how question is, what is the actual question, and then we'll stop. Can you tell about the zero padding of time domain signal for FFT and STFT? So because the size of output is more and then input, and if the size of xn and hn are different, at that time zero padding is required. Generally, if the size of input and the filter is same, then the zero padding will not be required. So zero padding is one way is just to add zeros to make the size similar. Second way is just to replicate the corner values. So in MATLAB, these two different methods are available that you can replicate the corner values of xn and hn, means last values of xn and hn, just to make the size of both signals to be same. That is the second way of zero padding. And other way, another way is also there based on some algorithm, so that I can tell you later on in the image processing filtering. I will tell you in the image processing filtering. Okay, sir. If any other question is there, I will take that. Otherwise, we will stop.
Yeah, thank you, sir. Thank you.
Okay. Thank you all. Thank you so much for.
Thank you, sir. Thanks to all participants. Thanks for participating. Thanks for your queries. I hope the session will be good for you. If you have any suggestions, you can write in chat box or in WhatsApp group, so that we can go through those also. Thanks to all of you once again. and good night.